So if anyone has any questions as they go along, can you type them into the YouTube chat window? And I think Ryan is going to be monitoring that window as well. And at the end, we'll have a question and answer. He will read the questions, and the relevant person will take a stab at answering the questions. So, just about to start. I'm going to start the local audio recording here. And it's 2 o'clock, so welcome everyone for this presentation from the MFMP. This is a story, this cab story, and it brings together a very large amount of our history in quite a succinct fashion. But the presentation's short, so this isn't going to keep you up all day or night or wherever you are. And it's direct to the point. So what you're looking at the top of the frame there is 3 different parties, A, B, and C, and a relevant image from each of them, which we're going to talk about in this presentation. So the cab story is greater than the sum of the parts, essentially, is what we're saying. So let's get going. Okay, Party A. Due to other world events on that day, Party A was moved to tell us about specific reactions that were highly predictable based on their most successful excess heat experiment. Party A shared full plans of the experiment and previously undisclosed details surrounding the event that produced those results, and they discussed risk with us. We were shown data other than that which was already in the public domain. Due to the other group investing, due to another group investing at the same time, the MFMP were prevented from replicating, which was a huge disappointment. So that is Party A's story. Now, before we move on to the other parties, B and C, I want to introduce the work of Alan Goldwater and the MFMP with the glow stick series. Essentially, 5.2 was the most interesting experiment we had. We saw this kind of signal, which looked like a big beta burst, and this is possibly due to breakdown of a charge cluster. That's one potential option. It certainly had the sort of effect of that happening, according to Shoulders, but this led us to think about radiation and really upping our game with radiation monitoring. So that led us to purchase some neutron bubble detectors. The next experiment, 5.3, was essentially a complete replication of 5.2, but to see if we saw any neutrons. And we did see neutrons, not fast neutrons, but it seemed that we saw a very small number of thermal neutrons in the temperature range similar to Party A during their experiment, which produced a lot of excess heat. So following our announcement, and obviously it was live when we were showing those bubbles appearing, I was actually in the room and Skip was in the other room, and it happened right in front of my eyes. Other researchers re-reported or reported seeing neutrons. So it kind of like was a bit, for us, it was a bit of a watershed moment, rather. And there were a couple of other people that kind of informed us of where other researchers had seen neutrons in the past, but it's not something that people like to publicly discuss. However, that being the case, Bob Higgins went ahead and developed a 3 helium-based open neutron detector. So that brings me to Party B. Party B made very specific claims of high heat. That's high excess heat. We knew and had known fuel feedstock. We knew the processing, and we knew the reactor design. All of those aspects were published. Subsequently, evidence was found in 2 scenarios supporting claims of both Party A and Party C. Party C. They claimed success in triggering LENR with excess heat. Due to timing and choice of reactor and technology, a hugely disappointing live test with no excess heat result was obtained. However, merely because and simply because that happened, because there was a lack of excess heat, we made a request to this party to say, look, you know, have you got samples from your previous reactors where you think you've seen excess heat or something interesting? And so under the circumstances that, you know, we'd had such a disappointment there, this party agreed to share access to samples from previous experiments. We made a specific request to this party about which samples should be focused on. And as it turns out, and you will see, only the samples highlighted for examination were interesting. The key sample with same key fuel elements as Party B support the claims of Parties A and B. Okay. So what we've got is we've got 3 independent parties in 3 different countries, and none of them knew what the other ones were doing or what the apparatus were, and they independently support each other's data, and now we're going to come on to that. So the cab story, we had no proof of what Party A was saying until recently. So whilst they had told us what had caused their excess heat, and it's never been disclosed before, we had never disclosed it. We didn't know if there was any truth to it, and of course, you know, that we didn't have any evidence other than the fact that they were showing excess heat and they had signatures to point to what they were claiming. Given the sequence of events and the nature of our project, we must inform at this stage. We've agonized over this for many years, but like I said just now, we didn't have any real proof that this was going on. And we've got to a point, as you'll see, that we have to release the information from the other parties B and C. And given our own experience, the whole thing means that we're in no position to release the information from parties B and C without also releasing the reason why people need to seriously think about what's going on. Proof is evidence that is so strong it would be statistically unreasonable to deny it. Now, you need to ask yourself whether the evidence we're going to present to you is sufficiently good enough to be considered as proof, or whether it is a good guide towards the possibility of establishing proof. So, Party A was Francesco Piantelli in January 2015. Now, we must thank everyone that supported us to go and see that esteemed researcher. For us, and I think you'll agree maybe when you understand that this is probably the most important thing that came out of that. However, the story is that following the first Paris attacks, Piantelli was adamant that the world could not be responsible with LENR, and he worried about an amateur researcher chancing upon a reaction that might cause injury, leading to a shutdown of the field. He explained that the highest excess heat that they had during their experiments was due to a reaction product that was released from contamination in his reactor's stainless steel. This has never been disclosed before. This took Piantelli a long time to establish. He explained to us that a common metal hydride could lead to the same active component, and that was a real safety concern. He had to tell us about this, firstly, because he didn't want to seem, you know, out of place, worrying overly about the Paris attacks, but also because we were going to replicate his system, and so he didn't want us to be put at the same risks if we made the wrong choice of stainless steel for replicating his device. We mused for years over if we should conduct an experiment as a fast track to Lena proof. But we were not willing to take the risk, obviously because of what Scintillator had told us, but others, practically speaking, we publish things as we go. And so if we were publishing and saying, you know, this is what we're planning to do, we know that in the past and historically, people have been following us step by step and have been taking it upon themselves to do the same experiment. And if we saw excess heat and so forth, then they might just go ahead and essentially, we didn't know whether the risks were real. And essentially, we still don't know whether the risks are real. However, at this point, we can't talk about B&C's data without telling you the whole package of information. So basically, it's neutrons. Okay, we talked about that in the 5.3 results, the thermal neutrons that were observed in a similar sort of temperature range to this experiment that was discussed. There's a link, and this presentation will be available, and you can follow that link to the paper that was published. But it was by far the most total excess heat, and by far the delta highest watts and temperature max of the Scintillator Ficcardi et al. Experiments series. So they were seeing neutrons. Now, if you actually go and look up on Stephen Krivitz's site, it's mentioned many, many times and discussions around it, but nothing was ever revealed about what the actual source of the neutrons were. This is the source of the neutrons. The source of the neutrons was vanadium-50, which is 0.25% of natural vanadium that was part of the steel of his reactor. The proton that comes out of the nickel, in theory, is going into the vanadium-50, and you can see the reaction chain there on the left. It might not be so clear now, but you will be able to see it in the presentation when you download it. That it goes to 50 chromium and releases a neutron. Okay. This has been a very difficult decision to make, and we all agreed as directors of the MFMP we would publish this because we have to at this stage moving forward. Moving on. Before we go into the evidence from players B and C, we need to clarify that EDS can sometimes confuse the X-ray between titanium and vanadium, between sort of 4.5 and 4.9. The data's on here, but essentially what happens is, and I've observed it when I was watching the university test the samples, if it basically is pretty sure, it'll show it as titanium, both peaks. If it's not sure, it won't show the second peak as vanadium. And if it's pretty sure that the second peak is basically vanadium, it shows that. At least that's what we observed. So, party B is Suhas-Ralkar. Now, I say Suhas-Ralkar rather than the ECHO reactor because actually, whilst he's using titanium and the titanium verifies to being titanium, and this is already published, when you look at his ash, and this is the ash from the pointy electrode, the cathode part of the ECHO reactor, you see sometimes that it can't determine what it is. So on the top left, you can see the second peak is not labeled. And the peak chart on the right is showing it as vanadium. Okay. So it would appear that there's some breeding of vanadium going on. Now, this may not be the case, but we are not about to go ahead and edit this data because the university did it independently. They have the data on their servers. You know, we have to give out the data that we have, which is the same data they have, and this is the charts that were produced. And given the fact that Suhas has claimed excess heat, when you look at what this does, then there's plenty of room for excess heat to appear. We have to present the data as is, and perhaps now you're starting to understand that if we put this out And everyone knows we started with titanium, and you're seeing some vanadium here. There's a clear transmutation, and it's nowhere in the rest of the fuel or the fuel raw materials. Party C is Me356. So like I said, very disappointing for timing or choices that were made. Anyway, the net result was we didn't see excess heat, very disappointing. However, as an opportunity to save face, Me356 allowed us to take away some samples. You can see the samples there on the left, and they're labeled on the right. Now, as I said, there were 3 samples when I asked him what we should focus on. He said, well, I'm interested in the electrolysis, the WH plus, and the nickel hydrogen 1 week. In actuality, his main focus was really, if there was just 2 he had to choose, it was the WH plus and the nickel hydrogen 1 week. Well, we looked at all of them, and this data we will share with you over the coming weeks. But the nickel hydrogen lithium tube, the nickel hydrogen lithium melt, and the nickel hydrogen lithium 3 weeks looked pretty much like the stuff that went in. The electrolysis does appear to have something interesting going on, but to be fair, anytime anyone says they're seeing any transmutation or whatever in electrolysis, someone always says it's coming from the environment and it's getting sucked onto the electrodes. So it's almost pointless showing the data, but we will share that data. The tungsten and hydrogen, clearly, according to Dr. Eagley, is a plasma reactor. And there's 3 plasma zones. You can even probably see it in the image, or you will when you download the presentation. And in each of those zones, the actual structure under the SMN is quite distinct. And there are various transmutations going on, which I think you might find quite interesting. The really interesting one is the second of the 2 that he asked us to really focus on, and that was the nickel hydrogen 1 week. Well, when looking at it, it wasn't just nickel and hydrogen. It was nickel and titanium. Clearly, you can see one of those things in that frame is not just nickel. Now, everyone is aware of, by now that are in this field, that the kind of spiky structure there is nickel, and it's filamentary nickel, and you can see that really there's nanostructures going on with the spikiness on that surface. Interestingly, this has been in a reactor for 1 week. Now, whereas we knew the reactor design, but we didn't, know everything about Piantelli's things, and we knew the reactor and the fuel and everything for SUHAS. In this case, we don't know what the reaction regime was, but we do know that there's hydrogen there, titanium, nickel, and that it doesn't look like it was in a plasma environment, because you would imagine 1 week in plasma, you wouldn't be seeing these very fine details on this nickel here. What are we seeing? We're seeing very high concentrations of vanadium reported by the SEM, EDS. So, again, it could be confusion between the peaks, but it seems to be a pretty strong signal in this case. So, why is this important? Well, 49 titanium is 5.41% of natural titanium. And with a proton into that, that breeds 50 vanadium, and that can give us the neutron reaction you can see on the branch on the right. 48 titanium leads to 49 vanadium, and 48 titanium is 73% natural abundance. The link across from 49, sorry, it goes from 48 titanium to 49 vanadium. That decays back to 49 titanium, but it has a 329-day half-life with a 601 keV. This presentation will have links to the reaction table and reaction charts with the kind of Piantelli reactions. it's quite nice. There's lots of different ways you can get energy out of here. You can see large gammas. You can see alpha particles coming off with good levels of energy. So it's understandable that if you had titanium in there, you might yield some high excess heat. However, the interesting thing is that 49 vanadium could appear as an isotopic tracer. That is to say that since 73% of natural titanium is 48 titanium, most likely output is 49 vanadium. This has 329-day half-life, producing the 601 keV gamma. So there's an opportunity of verification by long-term integration spectrometry. So the summary. We're already at the summary. Like I said, there's going to be a short presentation. Nickel plus titanium plus hydrogen and some form of electrons leads to, it would seem, excess heat, transmutations, potential emissions of gamma and neutrons, which could be the source of the excess heat. It seems to be resilient to reactor design. So you have Piantelli's reactor, which is not very high temperature, 300-400 degrees. He has his nickel coated nickel rod and the stainless steel enclosure, which has some vanadium in it. And so the protons are reaching that vanadium and producing the reaction. In the case of Me356 and Suhas-Ralkar, they have the nickel and the titanium in the reactor. Now, Suhas said that he got some slight extra excess when he added carbon, but really adding the lithium hydroxide and potassium carbonate didn't make much of a difference. So essentially, they had the same reactants in there to begin with, both Me356 and Suhas-Ralkar, which is nickel and titanium. Essentially, the nickel would appear to be the springboard, as Piantelli says, ejects the proton, and that interacts with the titanium, which has all kinds of reasons which we can come into later, or you might want to question about as to why it's very suitable. But also Suhas, if he processes, it would appear for long enough the titanium in the cavitation fuel processor, there is also a confusion as to whether it's seeing titanium or vanadium in the fuel if it's processed for long enough. Really, Suhas-Ralkar has managed to achieve 3 times transmutation in 3 different ways, and given the fact that you get different transmutations when you don't have lithium hydroxide and potassium carbonate in his fuel processor, it's almost like a Rosetta Stone of what happens when. Anyway, those all things can be expanded on. Really, the focus of this presentation is that we potentially here have a path to testing. Now, the situation is that this could be producing radiation that would be harmful. Therefore, you need bubble detectors, protection, that's something to slow down those neutrons, gamma spectrometry. This needs to be taken seriously. So, like I said, we couldn't, in good conscience, release the data from Me356 and Suhas-Ralkar, knowing what Piantelli had warned us, without giving full context to what this is. So you have 3 different parties, neither Me356 or Suhas-Ralkar, or basically anyone else in the world, possibly Focardi, and maybe whoever Focardi told, but and the other authors of those pieces of research. But basically no one knew this. And the observations of so when I went and visited Suhas and he told me he had titanium in there, I'm kind of like I'm taking a risk to take the video because there's no. My question was, does he have any radiation monitoring after he said he had titanium? I go, okay, well, let's just go and see it. And he said that no one had been in the reactor room bar him and 2 other people and me in the entire time that he'd done his research. So I was willing to take the risk to get the video because there was so little time. But I was quite frankly worried. That's why we spent so much time testing the neutron detectors and so forth with Me356, and why we bought extra neutron detectors. And the real test that I wanted to perform with Dr. George Eagley and Suhas in India, although at that time we hadn't told Suhas because we didn't want to color anything, was to have on video the neutron detectors, multiple neutron detectors at different distances, some moderated by water at different times, and turn the reactor on and off and see what we saw. We couldn't do that test. We did tell Suhas because we felt morally bound that he needed to know because he could be putting himself at risk. But like I say, there is no evidence anywhere that there are observable neutrons. But we have to say this because of the nature of the unedited data we're putting out with respect to the ash from Me356's nickel and titanium and hydrogen reactor and Suhas Ralkar's reactor in context of what Piantelli told us. So I'd like to thank everyone for listening. Now, if Ryan has got any questions, actually, I want to step back to the thanks, because I want to thank those people that supported Piantelli trip. Simply, we would not be able to know what potential people in the field would be at risk of had we not visited Piantelli and he had the courage to tell us. He knew that he had to tell us if we were going to replicate his device, because we may decide that we were just going to use the steel that was available and put ourselves at risk. So he had to tell us. Now, we didn't know because, as I said earlier, we were just going on his word for it. It was based on his theory and so forth. We didn't know until basically the day before I flew to India. And at that point, we really didn't want to color the experiments with Suhas Ralkar. We wanted it to be completely clean roomed, so he didn't know to plan for this. Anyway, as you know, that was a huge disappointment. For us, we managed to get the main details left about manufacturing the reactor, so there was some positives that came out of that. We also got a lot more ash to test. We actually have the sediment from his fuel processor unit, which is interesting colors, so I'm very looking much forward to testing that. But to cut a long story short, you have 3 independent parties, 2 of them doing things because they think it's just a good way to go, and we're seeing the same kind of results. One might reasonably assume that Me356 wanted us to test what was just labeled as nickel and hydrogen for running for 1 week as his top nickel and hydrogen experiment. We might have reasonably expected that he did that because that was one that may have produced excess heat. We have checked with Me356, and he says that the titanium is pure, that the assay is pure, and he never added any vanadium. Okay? We've already tested Suhas Ralkar's titanium, and we know that that tests as, at least for the bulk of the material, there are some contamination in that, but there's no contamination with vanadium. So we basically had to say what we've had to say today. So I'd like to ask Ryan now to verify that I'm not making it up. Ryan was the only other person that's an MFMP director that was in the room when Piantelli told us. I want him to just say what he feels that he saw and was heard on that day. So you're just not taking it from me. So Ryan, it's over to you before we go to the Q&A.
Yeah, your presentation of Piantelli's intent and what he said is accurate, is definitely within the best of my recollection, and I recall it pretty clearly. And he definitely has concerns about possible interreactions, and his recommendation was, or his vision of how it should be developed, is in a government and academic environment, so that all the potentials and dangers can be mapped, and then it can be channeled into something or the the safe versions can be put together. We're not taking that approach, and that other people aren't taking that approach, and so we have to be responsible and let people know what the risks are.
So yeah, we I guess we're at an advantage, but also tortured hugely by this knowledge over the years. On the one hand, as I said earlier in the presentation, we thought, we could just put some titanium and nickel in there and it would be a fast track to producing Lena proof. But because of the nature of the fact that we do our experiments openly, we don't do things behind closed doors, and people would be able to follow. They'd say, why are they doing this? And then maybe they might see, oh, we're seeing excess heat. But of course, at any point up until 5.3, we had no neutron detection, right? And we had no reason, because most of the world was saying you're never going to see neutrons with this. Okay, we only had the word of Piantelli at this stage. So when we saw neutrons, we upped our game, but we still weren't prepared to go ahead with something that would lead people into a situation where we didn't know, but there may have been a risk. Now we have a situation where we've got two independent parties, Me356 and Suhas-Ralkar, that did not know, because it's never been published before, that using titanium could lead to the observation of neutrons. But if you look at the reaction chains, there are many, many ways to get a lot of excess energy out of this. Now, it could be that in the case of Suhas-Ralkar, if he's got lots of charge clusters or the surface plasmons, basically some form of self-organizing electrons, that the gamma is dealt with. These 8.7 or 9.5 or 10 point whatever gammas you're getting out of these reaction chains is dealt with, and it's thermalized and so forth. We spoke about with Dr. Eagley, and his opinion was, like, a knife is dangerous. There are other very bad things going on in the world. And given the fact that we were required by the way we operate to publish, and publish in its entirety, the data from the analysis by the University of Me356's and Suhas-Ralkar's ASH, we could not publish that in good conscience without pointing out the obvious. I mean, it's the obvious that something's going on there, and you can look at it and see where there's protons involved, and you've got titanium and you've got vanadium, and then people will think, okay, you've got transmutation there. There's two parties that are seeing transmutation. Let's go ahead and make these experiments. It doesn't seem to work if you've just got the nickel. The nickel might give you your 1.3 times excess, But this is an experiment that could allow you to optimize. If you had all the proper precautions, that those neutrons aren't going to cause a problem for you, and the gammas are somehow dealt with, and they are high energy gammas, then you could be able to see, because you will be able to see these things outside of the cell, or when the cell is off, look at the 601 kV from the what is it, vanadium 49 to titanium decay, titanium 49. These things will be observable, so you will know whether you've had a better stimulation regime or a better pressure regime or whatever. And then you could use whatever you got as your working solution with other elements, like potentially, I haven't done the reaction chains, but I think probably people can assume that some form of positive ion can be taken in by some form of charge cluster. The minimum is Piantelli's 2 electrons taking in a proton. That's what he has in his experiment, so that's what he's going to get. So maybe zirconium, I don't know. It's very difficult to advise. What we're seeing in Suhas-Ralkar's fuel processor is seeing zirconium form, which is like stepping down from titanium. That's one process maybe, but then it's stepping across from zirconium to niobium, which is definitely not in any of the analyzed fuel components. So if people have now got questions, I don't know, Alan, do you want to come in and just, if this thinks that there's anything you want to miss, or just to say that as a director of the MFMP, you don't have any objections, or whatever it is you want to say. Do you want to come in there, Alan? Alan, are you still in the room? Okay, your mic is muted, so if you are speaking, we can't hear you.
Okay.
There we go.
I think you did an excellent job of presenting the material, Bob. Just for those people that came in late to this presentation, the entire video stream is being recorded, and you should be able to watch it from the beginning. Once we close the live stream, the video will still be available on YouTube. As far as the cautions that you offered, I think they're good cautions, and people involved in research in these kinds of reactors should take them very seriously, as we have. And if you can't afford proper radiation monitoring equipment, you can at least set up your experiments so that you're not near it when you run in the temperature regimes that we think could create a hazard. That's not to say that these things are automatically going to be dangerous, but that there is a risk of radiation that could be serious enough to worry us, and that you should keep that in mind if you go forward in this field, as we have done and will continue to do. Thanks for listening, and let's see. Check your email, Bob, was a comment from
it's just someone confirming that they've seen things with vanadium. So we've already got our first confirmation from a third party. I mean, you couldn't make this up. I mean,
yeah,
really. So people really need to seriously worry if they're just running into this blindly. Many, Piantelli told us he focused on nickel and hydrogen because the outcomes are safe and because he could run experiments for a long time, and he's not worried about the excess heat because he already knows how it works in terms of the simple hydrogen going into transition metals. Titanium is a brilliant choice if it didn't do this effect, because it has valency of 4, it's very low ionization energy, it's reasonably low electronegativity, it is a low mass element, which means adding a proton to it gives you bags of energy, and you can see that in the reaction tables. Also, vanadium and chromium, they're all fairly low ionization energies and also top-level transition metals. So you've got all kinds of different reaction chains that also step back. I mean, some of the reaction chains step back to, I think 46 titanium or 47 titanium, and you release alphas. So you've got a bit of recycling of the material in round loops with just eating protons and converting it to alphas, which, of course, would end up with helium. So from that point of view, that's all great, but this kind of reactor, if it does produce these neutrons, is not the sort of reactor you're going to want in your hallway heating your house, okay? But it could be, for responsible researchers, an approach. But given the fact that there are a number of researchers that might look at what we've already published about Suhas Ralkar's reactor, we absolutely had to make this public. It's been a really difficult thing. I really wanted to be able to show, in one respect, I wanted to be able to see Suhas Ralkar's verified excess heat and see no neutrons. But from my point of view, no one's going to accept excess heat until it's cooking their eggs and making them cups of tea, and they're not using a lot of electricity for it. But we've been told countless times transmutations and some sort of emissions. Now, I think Suhas has become the master of transmutations. That seems to be fairly clear. This combination of sound, high intensity ultrasonic sound, and some sort of discharge, whether it comes from collapsing bubbles or whether it comes from direct discharge or glow discharge in an highly transient situation. He seems to have got every angle covered there. But But in this case, you know, it would have been nice to just show the neutrons, turn the reactor on, see the neutrons, and by the way, don't play with this at home, kids. So yeah, people don't see the gamma. Piantelli does say he sees the gamma, but some of that gamma, what he did was, and you can see it in the report that we will link to, but it's already published, and it's published in 1994, or whenever it was, 2004, 1994. It's from the 1994 work. He used gold foil. The gold gets activated with neutrons, and that produces a 350 to 400 keV gamma, something like that. It's in the paper, and that you can detect. And by putting the gold foil on your reactor and knowing how far it was from the source, in that paper, and I think in Stephen Krivet's review around this neutron subject, he calculated that the flux from the reactor during operation was around 6,000 neutrons a second. That sounds like a lot to me. I only saw 2 and I was worried. So
what's the effect?
Sorry,
yeah, you got to multiply that times the effectiveness of the
okay, so
little tube and then the circle.
Yeah, the 2 might have been quite a lot when you look at the whole scheme of things. And you know, maybe my head was exposed to a few, but probably less than I would be exposed to in a flight. But the people need to be aware that this is the case. There's enough reaction chain products there that would seem to be supported by Piantelli's conjectures, or not conjectures, it's actually reasoned thinking based on hard evidence, that would yield excess heat. And you have 2 other parties that are claiming they've got reactors with excess heat that are using this combination of fuels. So like I say, I would look for low mass elements. Actually, in Piantelli's paper, that exact paper, he basically says, you know, we didn't see scandium, titanium, and vanadium. And it's kind of like almost saying they're not very good, when actually they're good, but they're not good because this happens. And so it's kind of like semi in there to don't look at there, look over here type thing. But anyway, we've said it now. We had to say it. So are there any questions out there?
Are there notes available from GS4 or only the video?
GS 5.4.
5.4.
Maybe, I don't know. Well, I'll have to look into that. Let's get back to you on that. It was some time ago. So many experiments happened since. So. Anything else?
That was it. So altogether, the data is encouraging that there is some interesting stuff going on, and it's definitely worth continuing to try to test, or especially try to validate the researchers that are making that happen. So it's encouraging that way. It's not rock solid. My criticism of it is we don't have tight chain of custody. We don't have the fuel before, or the ingredients and the fuel before and the ash after.
We don't have that in 2 cases, but we do have it in Suhas Ralkar's case. I do have one provision to add to that. Just let me say it. That we've never been provided with the titanium hydride because he was worried about shipping that. So maybe the titanium hydride has got some vanadium on it. But taking everything in the round, the evidence that was not public and shared with us as a point of concern from Piantelli, then the evidence of excess heat, and certainly when you compare the steam output from Me-356s and everything that Suhas has said has checked out in time, even down to the fact that Dr. Eagley thought you wouldn't be able to get the plasma going if the hydrogen was, not at a very low pressure. Maybe, Alan, you want to talk about your experiments that you did in 2013 that add some background to that.
Which experiment was that, Bob?
Where you added sound to your discharge tube. Are you there, Alan?
I am. I'm looking for my video feed. There
Yeah,
we go.
the video's coming through lovely.
Yeah. I did some experiments driving the glow stick reactors with a high-powered audio amplifier that was operating in Class D mode, which is a 300 kilohertz square wave that's modulated. So the output waveform has a very complex, messy set of harmonics going up all the way into probably near a megahertz. I did not try that with an active fueled reactor. It was a test of the glow stick system, and it seemed to work okay, but because the fuel that was in there had already been cooked pretty well, I didn't see any excess heat. It's on the list, and David Daggett at Phonon Research is currently also working on that plan at lower frequencies. I think he's going up to 50 kilohertz. And as a side note, I've put the links up for the GS5, the live document and the data archive. I can't put up an actual clickable link, and so you'll have to translate from where I put .dot, just put a period in there instead. Thank you, YouTube, for that. It's very convenient.
Yeah. We got another question.
I'm not the only one that has that complaint, I'm sure.
Yeah.
Any more questions about glow sticks and stuff like that? No.
One on the, do you have the frequency, the ultrasonic frequency, but I think you covered that.
So the ultrasonic frequency for the fuel processor is 19.46 kilohertz. It's slightly higher for the primary processors, which is just a single cup with one ultrasonic horn. That was published more recently, and it's all in the MFMP STEAMit. The main part of the processing, when the final fuel is processed in smaller batches, is at 19.46 kilohertz. That's from three 1.5 kilowatt horn transducers combination, and that is 4.5 kilowatts in total. The fuel is processed for up to 200 hours. And this is interesting, it would appear that if he doesn't add the, and this is a killer piece of information potentially as well, if he doesn't add lithium hydroxide and potassium carbonate to the fuel mixture at that stage, he tends to end up with the reaction products that you get from the Leclerc, i.e. lots of lead and niobium and things like that. They're kind of Leclerc peaks. If you take that and add in the lithium carbonate, lithium carbonate and potassium hydroxide, you don't get so much of those heavy metals. This is early days on that, and that needs to be a lot more thinking done on that data, and we've got a lot more to fuel and ash to look at now. With regards to the foil processor that seems to be producing precious metals like palladium and gold and silver, amongst other things, but that is using 300 kilohertz, and it's got a between 160 or 200 volts discharge with a gap, but everything's very well specified in the STEAMit. The actual reactor itself uses 1 megahertz, but it's tuned, and typically as the pressure and temperature changes within the reactor, you need to change the temperature of the actual reactor components, like the alumina and the head of the ultrasonic horn. You need to have a feedback loop that keeps the overall sound pathway in resonance, and that can vary plus or minus around the megahertz by 5% or whatever it is, so 50 kilohertz, I guess, up and down as necessary. So it tunes itself to keep most of the energy going to the reactors, and that's the case with all of the different ultrasonics that are used. And typically with ultrasonics, they come with a system that does this tuning, self-tuning and adjustment, because when, for instance, the fuel processor gets hot, there will be some shift in the speed of sound through the horn structure. So those are the key frequencies. But it would seem any kind of ultrasonics is a good start to get some transients and dynamics into your system. But I wouldn't bother trying to invent your own stuff. Suhas has done it. It's been laid out. And you pick your transmutations, basically. When you get all the data, you know, maybe you can argue that this is contamination or whatever, but I mean, certainly for the lead, there's a hell of a lot of lead. It's like you must have been chopping up chunks of lead and putting it in there. And it's the same kind of thing that what's his name, Leclerc sees. So go on, Brian. Is there anything else?
One guy was asking if Inconel and Monel, looks like asking if we've looked into them they have chromium, and I think all stainlesses have chromium, but we can definitely look at that. I'm not sure that makes a big difference.
Well, Inconel, I think, was used by one of the Japanese researchers. I published something on this about 4 years ago, and they saw excess heat, and it may have played a role. And we discussed using it because it's a standard powder for direct laser metal sintering. So we considered making reactors out of Inconel where the actual reactor body was also part of the reactive surface. But given the fact that we've seen this data from 3 independent parties, 2 of which did not know the research of the first and primary source, I would start by assuming that at least some form of charge cluster can get at least a proton into a nucleus of a transition metal. In that case, you need to really think about what the reaction products are and where it can go after you've done a couple of A, B, C steps, and just make sure that you're not getting any potential bad stuff coming out. Anything else?
There aren't any other questions at the moment.
Okay. Perhaps I will look on ECAT World, see if there's anything there. So again, I thank people that supported the PN Teletrip. I really need to thank everyone that supported the Echo trip, because if the Echo trip hadn't raised the money, we could never have tested these ashes, because we wouldn't have had the money to test them. And if it hadn't have been such a apparent failure in terms of excess heat, not in terms of the quality and capability of the equipment that Ryan and Brian and so forth had built, but seeing no excess heat, I had asked me 356 if we could look at his ash before. That hadn't been forthcoming, but there was the failure of not seeing excess heat on those days, and it would seem that the ash was provided to see if these claims of previous excess heat were real. And he did pick the 2 that look like they've got some transmutations, and the one that he's most interested in, which he didn't even label as having titanium in it, seems to be in this family of experiments. So my personal gut feeling, and this is not scientific, is that Me356 really has seen excess heat. He showed the charge cluster effect of the glowing metal when he says he turns the stimulation on a couple of years, a year and a half ago or whatever, which I discussed the other day. This is the same thing that interested Suhas Ralkar when he was doing his metal processing, this glowing metal. So I believe that there's strong evidence that both of them have seen excess heat. There's evidence from the data and the ash that they've both seen transmutation. Me356 has reported observing very large counts of neutrons in some experiments, or when they're driven too hard, so we don't know what he was using, because he's not told us for those experiments what he was using when that happened. And he's seen gamma as well, or photons. So my gut feeling is now, having looked at the ash, I think that's probably happened to him a couple of times, for sure. So that's really where we are. And you can debate whether these people have seen excess heat or not. the point about this presentation today, and why I feel it's different from anything we've ever done before, is because there is a real testable thing you can do here, but you need to be tooled up to do it properly. This is not something that you take lightly. It needs full risk assessment. You need to be having the right equipment. You really need to understand what these energies and the potential yield. I mean, you might have 10 reactors built that are not very good at creating the effect, and then you might have one that's very good creating the effect, and it's like, yay, oh, that's not very nice for me though, is it? So you need to be aware of the risks, really, and that's probably the most important takeaway from today. And then when it comes to Suhas Ralkar, again, we got those ashes because we didn't go soon, because he kept telling, no, I want to sort my banking problem out. I want to sort it out. And so I'm saying, well, you know, whilst we're waiting, you know, we do have some money to do some ash and fuel. Let's do your complete fuel process, sorry, your raw materials, fuel, and ash analysis. And he tried to send it once, it never came through. He then did it again and sent a second batch through, and that did come through actually on the same day that I'd already booked, the day before, 2 days before I flew to India. And only because only because of what's happened over the years has this thing that we can tell you today become possible. As I say, you can debate away the excess heat. You can debate away whether the transmutations are real, or you can say that it's just a problem with the EDS, right? But you've got three people, Piantelli, his reaction is, with Ficardi et al. That was their most successful reactor. Way more excess than any other experiment they ever did. Okay, so that's number one. You have Suhas Ralkar claiming his excess heat. That's number two. And you have Me356 saying, this is the best of the bunch. I want you to look at this. And this is the one that has the same things going on. So basically, every major thing you guys have supported have led to this point where we can at least advise you that now there is a possibility of having really good proof of LENR and something that's testable, but you need to be in a position to responsibly do these testing. As I said earlier, for those that missed it, we had to reveal this information given the fact that people knew that we had tested these ashes, and we had to reveal what the risks were, even though we weren't able to determine them by running the neutron tests on the Echo reactor. It may very well be that there are no neutrons on the Echo reactor because it's got the plasma in there and the glow discharge and the exciting, I don't know. But it may not actually be yielding the neutrons, and it may just be giving us the excess heat, but we cannot say that. And you see it there in the reaction tables. It might be that the neutron flux is so low because you're getting so much energy out, you only need a little bit of things to go, because you have to start from titanium and you have to get to vanadium first. And you might only have a few atoms of titanium 49 going to vanadium 50 once in a blue moon, and then you've got to have the reaction between those few atoms that are sparsely placed going and doing this reaction. So, there could be quite some time. Maybe if you started with scandium, you're even further away from when it goes bad. I don't think. Is there any more questions? Ryan, do you want to add anything to that?
I think we are pretty well covered. I don't have much to add, and there's no new questions out there.
Good. Okay. Well, I think it's about nearly just an hour, the presentation. I think it's probably a good place to stop it. Anyone should be able to look at the presentation almost straight after. I think there was probably about a 10-15 minute dead space at the beginning, so it isn't as long as it first seems. The main presentation is really quite short.
It is. It's 15 minutes of quiet time at the beginning. Okay,
good find. And what we will do, we will publish the presentation link for people to download as soon as this presentation's over. and you can look at it and follow the links to Piantelli's paper, to the reaction tables. Now, we're not experts, okay? We don't work at SOAN and stuff. So, you know, we've just used the National Nuclear Data Centre's particle collisions. Now, Dr. Eagley says, LENR does not work like those. And that might be the case. Maybe there isn't these neutrons coming out. There is just a transmutation, and it's just the energy gets released as electrons or phonons or whatever, just light. But, you know, you are getting that transmutation. We do need to say that this may be a risk, and Piantelli did observe neutrons. We observed neutrons. Me356 observed neutrons. Suhas had nothing to look for neutrons, so we wouldn't have observed anything. Moving forward, we are probably going to use the approach of Focardi and Piantelli, which was to use gold foil, because we can sit that accumulating during the whole time that a reactor is running. So even if there's not that many neutrons coming out, it will activate the gold, and then we can use that because you have a square area at a set distance from the reactor. You can even embed that gold somewhere in the insulation in, say, the Echo device, so that you don't have to have it on the outside. It can be there getting a little bit more of a solid angle. We can then assess what that means at a distance, if there's any neutrons coming out, by using the germanium detector or whatever it is, the diode detector that they were using. Something similar anyway, when it's cold. There's no electric noise going on. So yeah,
I also have my lithium-6 iodide neutron scintillator. It's pretty sensitive, and it's immune to EMF interference. I've tested that.
Yeah, so
Nice.
That is a very good potential route, and it just depends whether Alan is willing to go down this route. But as I said earlier in the presentation, and people might have missed that if they came in late, there are four different pieces of apparatus that appear to be producing this effect. So it's almost like you put the nickel in at the right size, you put the hydrogen in, the titanium of some form in there, and you hit it with some sort of dynamic electric regime, and this is what you get. So it seems to be relatively easy from the point of view, and that's the worry. That frankly is the worry. So people need to be tooled up. So I think that's gone past the hour here. I'd like to get the presentation published for people to look at in their own time.
Sounds good.
So closing remarks, Alan.
I think we've covered everything really well, and I look forward to feedback from the crowd. I think once we pull these ideas together a little bit and condense them, we might have something that's worth passing by the crowd on the Professional Atomic Scientists Forum, which is the CMNS group. I can post it there once we have a document that we agree sums everything up succinctly. We could probably get 9 out of 10 people saying, balderdash, those reactions don't happen. And I won't name names, but there are a few people that whose minds are open enough that we might get some very useful information. Just an idea, Bob.
Yes.
Mm-hmm.
Ryan.
Yeah, I'm looking forward to the feedback, and I want to go measure stuff now. Lots of good, interesting theories, but let's go measure it.
Yeah. So from my point of view, I really hope that we get to test the Echo reactor at the beginning of September. It's a real shame that Me356 couldn't prove LENR. It's a real shame that Suhas Ralkar couldn't, and even Piantelli. But I think as a combination between them, they've got pretty close. And as I said to you earlier in the presentation, it doesn't matter what you think about our professionalism as an organization or about us individually. It doesn't matter what you think about the people that have been referred to in this presentation or their capability. It does not matter. What we are showing you is the raw evidence. That's just the evidence. And what this points to is something that can be tested. And nature will only give the same result every time. So it won't be a matter of opinion. It'll be what the result is. And so it doesn't need to be about excess heat. Our primary goal of the MFMP was to demonstrate low energy nuclear reactions, right? This has the potential to demonstrate low energy nuclear reactions, but you need to play safe. That's what I want to end with. So thank you very much for everyone that supported us on these various trips. I look forward to your questions. Thanks, Ryan. Thanks, Alan.
Thank you, Bob.
Thanks,
well done.
Thanks, everybody.
Bye now.